Chapter 1. We're done with P. Some of you are glad. Chapter 1. And for Chapter 1, we are going to just focus on functions. Okay? We're going to focus on functions. Functions is a very important part of math, of pre-calc, of calculus. Calculus is a lot of functions. In this chapter, we are going to do domain and range. We're going to do increasing, decreasing functions. We're going to memorize the 12 basic functions, the graphs of them, so that when we have a non-calculator graphing section, we know how to graph them. We're going to shift them around. Hold on. We're going to do composition of functions. Remember f of g of x, g of f of x, fog. We're going to do some transformations and some modeling. Yes?
Does that show up on the SAT without graphing? I mean, without your graphing calculator, but you have to graph?
I think the SAT, there's a section that's non-calculator, isn't there? Yeah, on a regular SAT. Yeah. So, I know. I'm getting you ready for that. All right, so here we go. We're skipping 1.1. We're going straight to 1.2. And we're going to learn today, 1.2a, sorry. We're going to learn today about some properties of functions and just what a function is in general and how to find domain and range and continuity of a function, stuff like that. Okay? So I've got 3 parts for you today. 3 parts. So first part, letter A. And we're just going to talk about what a function is, how to figure out if something is a function. And functions are fun. It even says it right there, the first 3 letters. Fun, functions. No, not at all. You know what's not fun? Not functions. Conic sections, a lot of those weren't functions. Did you like that chapter, chapter 10 last year? Okay, so let's first start off by saying what a function actually is. So a function is a rule. It could be an equation, it could be a t-chart, it could be a graph. It's just a rule that assigns is that how you spell signs? Yes. Okay, good. Every element in the domain, and I'm going to talk about what domain is in a minute. A rule that assigns every element in the domain a unique means different, right? A unique, that spells unique, by the way. It's gross. A unique element in the range y equals f of x. All right, there's very fancy definitions of what a function is. That one's not very fancy, okay? Basically, it's saying this, and you might have seen this before. Suppose that you have this function machine. Have you ever seen a function machine? Yeah, and it's spitting out all kinds of stuff. Okay, and so x equals some number is going into the function machine, and this function machine is changing it by using some weird function, or not weird, normal, and then it's coming out as a y value, right, or f of x, okay? So x is going in, and for every x that goes in, you're going to get one y that comes out, a unique y. So for example, if I plug in x equals 2 into this function machine, I could get an output of y equals 8. Maybe it's the cubic function. Maybe it cubes everything. But if I plug x equals 2 into the same function machine, there's no way it's going to give me y equals 9. Okay, that's impossible. When you plug in an x, it gives you one unique y. Okay? Now, if I plug in, okay, so this, no bueno. If I plug in x equals 5, and I get y is 25, and then I plug in x equals negative 5, and I get y equals 25. That's okay, though. Okay? That's okay. See, 5 went in, it was only one thing that came out. Negative 5 went in, it was also only one thing that came out. Those things were equal to each other, but it doesn't matter. That might be the squaring function, right? Inside the machine, it squares everything. Okay, So now let's talk about what domain and range are. Still on point A, domain and range. You did this a little bit in Algebra 2, not too much. Back when I taught this 15 years ago, domain and range, that was huge. We spent a ton of time on this stuff. Domain, those are the independent variables. Independent. It's the independent variable. So like, see that machine I was talking about a minute ago? I can take whatever I want within the domain, or like we're going to talk about, sometimes it's not whatever you want, but it's independent. I choose this number, I plug it into the function machine, and output is my dependent variable. Okay? My range depends on what my domain is. I plug in 2. That number that's coming out depends on whatever that was coming in. The domain are going to be your x values. The range are the y values. Do you remember domain and range a little bit? Yeah. What else? The x values cannot repeat. We just talked about that a minute ago. Like if I had the 0.25 and then I had the 0.27, that can't happen, okay? But these can repeat. You can get repeat ranges coming out of the function. Like when I plugged in 5, I got 25, and when I plugged in -5, I got 25. Okay, now we're going to be able to tell if a relation is a function or not, okay? And we're going to use a test on a graph, okay? So if I look at the graph, or I just picture the graph in my head, because sometimes I'm not allowed to use my calculator, but I know what some shapes are like. Maybe I may not know exactly what the points are, but I know what the graph kind of looks like. So if I graph something and I want to tell whether or not it's a function, I can use a test. Do you remember what that test was called? Yes, the VLT, which is not a sandwich. What's V? Veal? Vertical. Okay. I was thinking of a sandwich. What is veal? Is that like baby cow or something?
Yeah.
Oh, nasty. Gross. Venison. That's deer. Some deer meat sandwich. Yum.
Deer bacon.
Yes, deer bacon. Gross. Okay. Well, ew, gross. Now, vertical line test says that a graph is a function if the vertical line only touches once. And you've just gone like, yeah, I agree. Okay, have you ever like thought about why? No? Yeah? Okay, let me give you a sideways parabola. A sideways parabola is not a function, okay? It's not. We learned these when we did conics last year. If I were to draw a vertical line on the graph anywhere I want, it will touch 2 points. What that means is whatever this x is, let's say this x is 2. And I'm getting x is 2, y is 4, or -4. Am I allowed to put something in as 2 and get 2 things out? No. Okay, that's why the vertical line test is so nice. You don't have to think about what's going on. You just do a vertical line test in your head, and you got the answer. So let's do some. Number 1. Yes or no? Is it a function? Yes or no? Okay. No calculator. No calculator on this one. You have to think about what it's going to be. How about y equals 5x plus 1? Is that a function? Now, you don't have to really like sit there and, okay, I got to go to 1 and it's up 5 and over 1. You can just picture, like in general, what that graph's going to look like. What is that?
Linear.
It's linear. It's a line. And it's a slanted line. Okay? And all slanted lines are functions, yes or no? Yes. Okay. Now, here's the question for you. Are all lines functions? No. What kind of lines are not functions? Vertical. Vertical lines are not functions. They fail the vertical line test at every single point, right? Okay. They like majorly fail. How about something that you studied quite a lot of last year? Y equals x squared plus 3x. What's that the graph of? It's a parabola. It's a parabola that opens up. Are parabolas that open up or down, are those functions?
Yes.
Yes, they are. And we studied that a lot. Ooh, no more cowbell. What was that? Nick.
Sorry.
No.
It's mine.
Okay, let her see. All right, how about this? Last night I was actually talking to my neighbors about this, and they told me to go away. their kid was riding his bike. And his bike, he had lights on the spokes of his bike, and then he was riding it. It was really late. It was like 8 something. And it looked like a circle when he, well, the street lights were on. It was like 8 something, 8:15 maybe. Anyways, and I said, oh, that's like, well, x squared plus y squared equals 4, because it looked like the radius of the circle was 2. So when you have x squared plus y squared equals 4, yeah, that's when they told me to go away. That's just a circle, right? That's a circle. We learned that last year. Did you remember it? Okay. That's going to be a circle with radius 2, which does not pass the vertical line test. So circles are not functions. Circles are never functions. Okay. I'll tell you a little hint, though. Pretty much anything that has a y squared is not going to be a function. Because if you think about it, if you have x equals y squared, then when x goes in, you get 2 things. Yeah, you get 2, right? You can think of this as, well, I'll solve for y. And if I solve for y, I get plus or minus rad x. Okay. Let's move on. Yeah, no, they're good. They're really nice. I hope they don't subscribe to my YouTube channel. Okay, letter B. No, they're super nice. Actually, they offered to give me the lights for the Moonlight Madness bike ride that I'm doing next Wednesday night. 8 to 10. It's the full moon of the month, and they do this bike ride in Long Beach, and I'm going to it. It's on Facebook. You can join if you'd like to. All right, domain and range. And they always have a theme. And this year's theme is you're supposed to dress as your favorite literary character for back to school. I'm like, yeah, right. I can't even name a literary character. A math test book?
Like a textbook.
Ooh, like a math. Yeah, I could wear my big calculator.
Hold your big pencil.
How am I going to ride a bike, though?
Put it on your handlebar.
I don't know. It should be fun. Yes. Yeah. So that should be fun. Next Wednesday night, there's a full moon, and there's a bike ride in Long Beach. The whole bunch of people. And they're like,
I'm gonna have math
oh,
homework.
that's true. I will. Wednesday.
Yeah, I'm gonna do my homework when I get it.
Yeah. On the side. That's terrible. All right, now we're going to do domain and range. Okay? So let's focus on domain. And domain are going to be the x values that are allowed in your function machine. Okay, because function machines are sometimes, you can't plug whatever x you want in. Okay? Like, for example, if I had a function machine here, I like making these function machines. They're very weird. If I had a function machine and my function machine was the square root of x, and we're only doing real numbers, and I decide, I want x to be negative 100, and I'm going to plug that into my function machine. Am I allowed to do that if we're dealing with real numbers? No. What do you get? Yeah, you get Nick's girlfriend. She's a perfect 10, but she's imaginary. He's not even listening. All right, 10i. I did the perfect girlfriend thing, you know? What? No, never mind. All right. Anyways, but you can't have that. So there's restrictions, okay? So when you're doing domain, you don't want to think about what x can be, because there's an infinite amount of things that x can be. I want to think about what x cannot be, okay? But then you're not going to write it like that, sort of. All right, let's do some. I'll show you. All right, number 1. Number 2. Find the domain. Find the domain algebraically. No graphing on these, okay? You can graph in your head if you want to. I'm not going to, tell you can't graph if you know what it looks like. But we're going to just do some basic ones. Here we go. Let's do y equals x squared plus 3. And we're just doing domain. We'll do range in a little bit. Right now it's just domain. So I have to think about x, and I have to think about all the things that x cannot be. And this is the way I kind of do this in my head. I go through like a checklist. I say, can x be positive? Can I square positive numbers? Yeah, check. Can I square negative numbers? Sure. Can I square 0? Yes. Okay. And you knew this from last year. It was all reals. Okay? We did this last year. We did parabolas, and we did what was the domain of parabolas, what's the range of parabolas. And the domain of parabolas was always all real numbers. All right, let's do some more interesting ones. Let's do f of x equals the square root of x plus 3. Okay.
If we're given a problem like that, do you mind if when we're working it out, we just put y equals the square root of x?
Sure. No, not at all. Not at all. Oh, and by the way, that reminds me. All real numbers, you can write it as a big capital R like that, but the book will write it in interval notation, which is negative infinity to infinity. That's so extra, isn't it? So extra. I know, because they can't. There we go. Is that better?
Yes.
It's gross. I always do that, huh? I always do circles. Okay.
What is the abscess? Never mind.
All right, let's do part B now. What's the domain? Okay, here's how you do these. Now, you know not everything that you want to can get plugged into this, okay? But you can't just say, oh, let's start at -3, or -4 won't work. So you have to really do this in algebraically type of way, okay? So we're going to take this inside expression, and we know that that inside has to be greater than or equal to 0. 0 is okay. You can take the square root of 0. But you can't take the square root of anything less than that. So whatever's inside of the radical has to be greater than or equal to 0. And then when you solve, you subtract 3, you get x is greater than or equal to -3. Okay. If you want to write it like that, you can. But you can also write it in interval notation. There you go. See, that's why I don't do that. It's ugly. So -3 to infinity. I know, it's gross, huh? I need to work on this. I need to work on my penmanship on the iPad. It's really disgusting. All right, let's do another one. Another one. See. Sorry. G of x equals about 5 over x minus 7. Okay? So, don't think about what x can be. Think about what x can't be. We know, all of us know, we've had some math in our lives. We all know that we're not allowed to divide by 0, right? So x can't be what? 7. Okay, so this is how I would write this. I would write the domain would be all real numbers except for 7. Okay, I'll show you how the book writes it. The book does this. Negative infinity to 7 with a parenthesis, union 7 to infinity. All they're doing is taking out 7 there. Okay, but that's the way they write it. All right, you try this one. H of x is equal to negative 10 over x squared minus 25. Okay, you do that one. Find the domain of that function. These are all functions, by the way. Just find the domains of functions. And you don't need to write it in interval notation. You can write it the other way. Either way is fine. All right, you ready? So, what can x not be?
Plus or minus.
Perfect. Plus or minus 5 this time. Okay? So if you were to factor this, this would be x plus 5, x minus 5. So two things are going to make that 0 in the denominator. So all real numbers except for plus or minus 5. If you wanted to, you could have written negative infinity to -5, union -5 to 5, union 5 to infinity. Yeah. Who wants to write it that way? Anybody? Jerry does. Okay. Letter E. Jerry's busy. He's doing like lesson 1.4 right now. So, okay. Letter E. Here we go. How about J of x for Jerry? Here you go, Jerry. This one's for you. We're going to do the square root of x over x minus 5. Now we're getting more difficult here. More difficult. Okay? All right. That's a J. That doesn't look like a J to you? No, imaginary, that's I.
Why would it be an I?
That's J. How do you do J's? Like that?
That's it. Jesus fish looking down. I thought I said all real numbers.
That's alpha, and that's beta.
Look at your J.
And there's theta.
Is still recorded?
Oh, Oh, yeah, whoops. Whoops, whoops. Okay. Man, I hope nobody else watches this. Okay. So there's two answers kind of, but you have to put it together. So we know that x can't be what for sure? We know x can't be 5. Okay. But then look at the top. If I just say x can't be 5, that's not enough. Because I need to also say that x has to be greater than or equal to 0. It has like two domains in a way. I mean, it doesn't, but you have to think about it kind of separately. So what you should write is x has to be greater than or equal to 0, but not 5. Okay? Greater than or equal to 0, but not 5. And you could write that as 0 to 5 union 5 to infinity. No. Here's all. I love that. I love interval notation. Okay,
You would use that?
yeah, you wouldn't?
It's kind of nice.
Yeah, I like it. Let's flip that one. Let's do k of x. Let's flip it. And let's do x minus 5 up top with the square root of x in the denominator. X minus 5 up top, square root of x in the denominator. And we're finding the domain of this. So what can x not be, really? It can't be a negative number. Or it can't be 0 either, because 0 is going to make it 0 in the denominator. 5's okay. You can have 0 in the numerator. That's okay.
That just gives you 0 then, right? That's your final.
Yeah, that would give you 0. It would give you 0 over 5, which is 0. So x has to be greater than 0. You could also say positive numbers only if you wanted to. You could say 0 to infinity, but do not put a bracket around 0 because that would be wrong. You can't have 0 in the denominator. Like if someone comes over with some pizza, right? You can have 0 out of 8 slices of pizza, but you can't have 8 slices of pizza out of a pizza that doesn't exist. That's why 0 is not allowed. Okay?
What if you make the slices in?
No. Everyone always has like their own. What if? No. Okay, last one. How about the volume of a sphere? Do you know the volume of a sphere? Sure, you know it. 4/3, yes.
And then pi r.
Pi r cubed. It's volume. It's cubed. Yeah. Good. I use that every day. Nothing. I was kidding. All right. So, what's the domain given that r is the radius of a sphere? Sphere. You know what a sphere is, right?
It's like a circle but 3 dimensions.
Yes, it's a circle, but then you go like this, and then you draw a little thing in the back, and it looks like a sphere. That's pretty good. I only taught geometry 1 year. It's horrible. Okay. It is the worst. I don't like geometry. You liked it? No. Oh. All right, the radius is the sphere. Okay, now, when you do this problem, you think, okay, r is going to be the domain. Okay, it's like x, it's the domain. And I can cube anything I want, but it has to make sense in this problem. Can the radius of a sphere be negative? No. Can a radius of a sphere be 0? No, you have to have a sphere. Okay, there's a sphere there, and it has a radius, and so your answer would be r would have to be greater than 0. If it's just a regular old function, sure, r could be anything. But since it's something particular, like a radius, it has a restriction. Okay, now we're going to move on to number 3, and we're going to do find the range. And with finding the range, I let you use your calculator for this. Because range is a little difficult. You're not thinking what x can't be. You're thinking what comes out of this function and trying to decide what that can and can't be. Okay. So we're going to find the range. Yeah, get your calculator. I got to get mine. And we're going to find the range, and I only have like 3 of these to do. Okay. Letter A. F of x equals 2 over x. Okay, and some of you might be able to tell just by looking at that what the range is. What numbers would I get coming out of this function and when I plug in x values? If you don't, then you can just go ahead and graph it on your calculator. 2 divided by x and graph. Okay, and it looks like that. And we're actually going to graph these in chapter 2. 2.6, 2.7, somewhere in there.
Will we ever have it from like a non-calc?
Oh yeah, not right now. But when we do them, we will. We'll do these all by hand. They're very fun. Okay, so that's the graph. It's a rational function. That's what it's called. And basically, y is everything on this graph. All these y values are all working, and all these y values are working except for one number. What is it? 0. Perfect. Okay, so you would say all real numbers except for 0, or negative infinity to 0, union 0 to infinity. Okay? So not 0. And 0 is not going to pop out of that function because there's nothing that would make that 2 over x 0. You just can't. All right, try another one. Oh, this one you did in Algebra 2. G of x equals x squared plus 3. G of x is equal to x squared plus 3. You may graph this on your calculator if you need to. Some of you know what this looks like already. This is just a parabola that's been shifted up 3. We're going to get into transformations in this chapter. We're going to be really good at just like, I give you a function and you know what it looks like. It's fun. All right, so what is the range of this? Where does my y's start and where do they go?
3 and
Perfect. 3 and up. Y is greater than or equal to 3 from 3 to infinity. All right, let's do one more. You try this one on your own. Let's do m of x is equal to the square root of x plus 1. Excuse me. You can either graph that, or you can just look at it and go, okay, what's going to come out of this function? What type of numbers are coming out of there? Some of you. No, we're not doing any imaginary numbers right now.
will we get there?
We will, like, yeah, when we do polynomials and solving all the zeros of a polynomial, there will be complex
And like
numbers.
graphing complex numbers?
Yeah, we'll graph some complex numbers. Actually, complex numbers show up next semester when we do vectors and trig. Demov's theorem, super fun stuff. You're going to love it. All right, if you went to graph this, you notice that this is a sideways top half of a parabola. It's been shifted one to the left. And so what's the range on this? What are the y values that work? Y is greater than or equal to 0. Okay, let's talk about that real quick. The range starts at -1. See, these are the x values. If you look at range, think about like home on the range and you're walking back and forth, okay? Or range is this way. Domain is this way. So you're going this way on your domain, and you have -1, and then all the x's after that all work. Okay, so x is greater than or equal to -1 is domain. So look at the range now. Range is up and down. And you're going like this, nothing here. But as soon as you get to y equals 0, there's a dot, and then all these y's up here also have a value. So that would be from 0 to infinity. It's a very messy graph. Yeah?
Now, I don't know if this is the one, but isn't there like an asymptote where that y doesn't go above like that certain point?
Yeah, but not for these, not for those. Yeah, it'll keep rising very slowly though.
So when you're looking for range, I mean, you're looking for like what has a value and
Yes.
what doesn't.
Yeah.
Okay.
Exactly. Okay. Anything else with domain and range? All right, we're going to move on to the last part. This is part C, right? Yeah. Last part. Yep. Continuity. Sounds difficult, huh? Continuity. Okay, so we're going to talk about the continuity of a graph. A graph is continuous at a point if it doesn't come apart at that point. Basically, they say that continuity is a graph is continuous if you can draw it without lifting up your pencil. Okay. So there are 3 types of discontinuity. So once again, we're not going to talk about where is the graph continuous. We want to talk about where is the graph not continuous. So there are 3 types of discontinuity. So not continuouses, in other words. 3 types. There's actually 4, but we're going to do 3. We'll leave the 4th one for the calculus teachers. So number 1, and you're going to need to know these types. Okay. So the first type is called a removable discontinuity. Removable. It's like someone came over to your graph and they removed a point from your graph. Okay? So let me show you. Let's suppose that x is not continuous at some value a. Okay? We'll say a is right here. A doesn't have to be positive, doesn't have to be negative, it's just right there. So here's what my graph looks like. My graph's going along, it's a nice function, and then all of a sudden at a, there's a hole in the graph, but it doesn't jump up anywhere, go anywhere else. It starts back up and maybe goes somewhere, something like that. Some weird graph, who cares? Okay? But what this is there is a hole in your graph at x equals a. And that is called a removable discontinuity. Okay? Now, there could or could not be a point there. Right now there's no point there. But I could also put a dot right here. Okay? And that's okay. It's still a function. And there's still a hole in your graph. So it doesn't matter if there is a point there or there's not a point at A. Just there's no point on the graph at A right there. Okay? It's called a removable. All right, number 2. Second type of discontinuity is called a jump. And a jump discontinuity, let's say, once again, x equals a. There's going to be a jump in the graph there. So here's your graph. Let's do just like the last one. Okay? And instead of starting right back up where we ended off, you're going to jump somewhere else on the graph and start back up again. See how there's a big gap right there? See the difference between a gap and a hole? A gap, there's a separation, and a hole is just a hole in the graph. It's like if someone cut you and you have this big gap, or if someone shot you and you have a hole in your stomach. It's a really good visualization. Yeah, you're dead either way, but yeah, there's a discontinuity of your life right there. All right, number 3. And then there's an infinite discontinuity. And we've seen these already. And let's say at x equals a, there's a discontinuity that's infinite. That means that your graph might do something like this. It's going towards negative infinity, or going towards negative infinity, or towards positive infinity, or opposite directions. But there's an infinite discontinuity there because it's going to infinity or negative infinity on the y values. Yeah?
The jump one?
Yeah.
Is that black point supposed to be on that A
Yeah.
line?
It could either be filled in or not filled in.
But it has to be on that same X.
Yeah, it usually is. Mm-hmm.
So it's not going to
Jump over?
Yeah.
No. Mm-mm.
Okay.
That'd be different.
And then are there certain formulas for that?
Yeah. Let's do some. What number are we on?
Whoa.
I know, look at, that's all we've learned today. Hardly anything.
Stop it.
Just kidding. We've learned a lot, huh? Number 4. Does anyone take notes on their iPad? You like it? Yeah? All right, number 4. This is what we're going to do. We're going to find the x value where our graph is discontinuous. Find the x value of discontinuity, they might say. And the type of discontinuity that it is. So we're going to find both the x value and the type of discontinuity. Okay? If you're good at domain, you're going to have no problem with this. Because that's where your problems are going to be in the graph, is where the domain can't be a value of x. So we have 3. Ooh, we are running out of time. How about f of x equals x plus 3 over x minus 2. Okay? All right. So where's my problem going to be at? Just by looking at it. 2. Perfect. We know x equals 2 is going to be an issue. Okay? And we would go to the graph and we would graph it. When you graph this on your calculator, make sure that you put parentheses around both. Okay, so up top we have, what was it, x plus 3 divided by x minus 2. And we graph. So at x equals 2, there's something going on here where my graph is going all the way down towards negative infinity, all the way up towards positive infinity. What type of discontinuity? Is that infinite? Do you remember what's happening at x equals 2? What's that called? That imaginary line there? Yes, an asymptote. That's an asymptote. There's actually one horizontally at y equals 1, and there's one at x equals 2. We're going to learn how to graph all that. But right now we know that at x equals 2, there's something going on there where I was going along on my graph, and it was going just fine, and all of a sudden I had to pick up my pencil, and I had to redraw it up here. So there's a discontinuity at x equals 2, and it is infinite. And you're going to get your calculator for this, okay? You'll be able to have it. Ew, that's gross. Okay.
And the asymptote would equal 2.
Yeah, the asymptote is x equals 2. And we're going to do that next chapter, I think. I don't know if we do that in this one. All right, g of x equals, let's do another one. Oh, this is such a good graph. The absolute value of x divided by x. Okay? Yeah. I don't think you've ever graphed that before. That's kind of fun. Taking the absolute value of x and dividing it by x. Where's our problem, though? X equals what? 0. Okay. The domain of that function is all real numbers except for 0. So let's see what's happening there at 0. Let's graph this on our calculator. Absolute value of x divided by x.
Do you need parentheses there or no?
Nope. Ooh, fun. Okay. What this graph is doing is it's equal to -1. As soon as it gets to 0, it jumps up to +1. Oh, I just even said the type, didn't I?
Yeah.
All right, so at x equals 0, it's a jump discontinuity.
Why does it do that? Like, what's the reason?
Yeah, because, like for example, when you plug in, say plug in x is -2. You get a -2, which will be positive, over -2, so that's going to give you -1 every single time. When x is negative, it gives you -1. But when x is positive, it'll give you all the +1 all the way along. Yeah. Okay, last one. It's a lot for today. It's already been 37 minutes of notes. That's well, I mean, I talked a little bit. Okay. X squared minus 9 over x plus 3. Now, these are my favorite. I like these a lot. We know what the problem is already. We know where our discontinuity is going to be. It's going to be at x equals -3. And when you graph this on your calculator, you'll be shocked to see that your calculator doesn't agree with you. But they do. Parentheses, x squared minus 9. Ooh, that's really dark. Divided by parentheses, x plus 3. And when you graph this, it looks like just a straight old line. How is that a line? You think that? Like, look at this, x squared, and there's division. Anyways, do this. Hit trace. And let's plug in that problem. Let's plug in -3. What does y equal? Nothing. There's no value there. Okay? Now, your calculator doesn't do a very good job of showing you that. But what it did was, at 1, 2, 3, there's a hole in the graph, and it looks like this. You can't see it on your calculator unless you actually plug in -3. You see there's no y value there. So that is a removable. Don't call that a hole. It is a hole in the graph, you are correct, but it is called a removable discontinuity. Removable. And the reason why is this. If you were to factor the numerator, okay, what happens is you can reduce and you get a line. You get the line y equals x minus 3. But you have to take the original and say what the point is, okay? All right.